Swayam Prabha. Digital India. Educated India.
Welcome. So today we will start with Rankine cycle with regeneration. Now till time what we have covered is Rankine cycle simple without any attachment. Then we talked about Rankine cycle with superheat, and then we have said that there is Rankine cycle with reheat. So these two things we have seen as an attachment to the Rankine cycle. Now there is a third attachment which is called as the regeneration process that we are going to see here onwards. The concept of regeneration is actually taken from the concept which is existing in the Stirling cycle. So here we are going to discuss about what is Stirling cycle first. Thermodynamically we know that Stirling cycle is a cycle which is comprised of 4 processes, where we will have process 1 to 2, process 1 to 2 as the constant temperature heat addition from the external source. This is little important. This is constant temperature heat addition into the system from the external source. Process 2 to 3 is a constant volume process. Here we have V constant, here we have T constant. But here process 2 to 3 is V constant, but it is heat loss process also. But this heat loss is not to the surrounding. Then process 3 to 4 is the Q out process at constant temperature to the surrounding. And then we have process 4 to 1, which is volume constant process. But then here we are having heat gain in the volume constant process, but this is again not from the surrounding, but this is internal heat exchange from the process 2 to 3. So practically in Stirling cycle we have process 2 to 3 is a constant volume process. It is rejecting heat, and that heat is gained by the same system, part of the system which is executing process 4 to 1. So this concept is called as regeneration, where we are transferring heat from one part of the system to the other part of the system. The same diagram on TS chart is process 1 to 2 is isothermal heat addition, process 2 to 3 is constant volume heat rejection not to the atmosphere, process 3 to 4 constant temperature heat rejection to the atmosphere, and process 4 to 1 constant volume heat addition again not from the atmosphere. So there are engines which are operating in this manner for the Stirling cycle. They are existing engines. We can see here that these engines can either be 2 cylinder 2 piston engine as in this case, or we have 1 cylinder 2 piston engine in other case. So there are different versions of Stirling cycle based engines. The point to be noted over here in either engines that here we are not having any mass transfer. The system is completely closed in either case. So it is not like our conventional internal combustion engine where we will have fuel added or we have exhaust. So the same gas, same matter is having heat exchange and work exchange taking place. We can understand this cycle in a greater manner if we consider a system of 2 cylinder 2 piston like this. Here the 2 piston motion is in phase. They are not moving in the same direction or in the opposite direction, but their motion is in having phase difference. So for some time they might move in the same direction, and for other time they might move in opposite direction as well. So consider the case which is process 1 to 2, which what we are calling it as constant temperature heat addition. So in this case, process of heat addition would take place, and in the process of heat addition we know that due to addition of heat temperature will increase, but we want temperature to be constant. So we will have this heat addition process clubbed with the backward motion of the piston, which is in the high temperature zone. So this backward motion is practically expansion, volume is increasing and then heat is getting added. But as volume is increasing, heat is getting added, these two things will get coupled and then we will have constant temperature. So this is constant temperature heat addition. In this case, second piston is almost stationary, where we will not have much motion of the second piston. But in the process 2 to 3, we have backward motion of the first piston, which is trying to push this gas in the second piston or second cylinder, and the second cylinder piston is moving backward and this is receiving this gas. This high temperature gas is moving from one cylinder to other cylinder, but in this phase this is a wire mesh or this is a buffer in which this hot gas will give its heat, and then it will come in this cylinder, which is low temperature cylinder. So we get the temperature lower here after the process of constant volume or constant volume. So in this phase we will have our piston coming to dead end and most of the gas would have arrived in this cylinder. Then we will have, since this cylinder is cold, we will have rejection of heat, but rejection of heat would be practically mean to loss of temperature, but loss of temperature would practically get compensated by compression process, and so we will have the temperature to be remaining constant in this case for the gas in the cylinder. But then in the next phase, this cylinder, as it is moving forward, this cylinder will try to come back. So the gas completely will move from this cylinder to this cylinder, and in this phase it will again take the heat which it has given to this wire mesh or buffer, such that in the motion of the gas for constant volume process it will regain the heat which is actually left out by the same gas. So the process which are constant volume processes, here we are talking about heat transfer in the constant volume sense, but not with the atmosphere. So system is keeping some heat, is a buffer which it is taking later on. Now this concept of heat addition or heat transfer from the system's different part is translated in the Rankine cycle. So we have seen that it is possible to have it within the system heat exchange, but then why regeneration is required? We have seen that external irreversibility can be reduced by reducing the pinch point temperature difference. Pinch point temperature difference, we had said that this is the minimum temperature difference between the steam and the flue gas, and that temperature difference if we try to reduce, then we will have lesser and lesser irreversibility. Then what we can do to improve the efficiency is we can increase the mean temperature of heat addition, and then for that we were going for superheating, but we have also seen that superheating may not be possible always. It depends upon the source of heat. So since it depends upon source of heat, what we can do is mean temperature of heat addition we can increase by actually reducing the temperature, if reducing the amount of heat added into the water in the economizer part. Since we know in the economizer we add sensible heat, and sensible heat is the heat where we are actually having change in temperature. So if we try to remove that part of heat addition, then we will just add the saturation latent heat or superheat. Then those two heats will have higher temperature of mean temperature of higher mean temperature of heat addition. So this is what the argument of regeneration. If we can fetch some heat within the system and we can give it to the economizer, then we can bypass the economizer. Then the idea in thought, it's not practical, but idea in thought is we know that we have pump. Pump is the process 1 to 2. From 1 to 2 we know that it directly goes to the boiler where we have heat addition in the boiler. This is what we were seeing till time, but now what we are saying that no, it will not go to the boiler, but it will go around the turbine. It will go around the turbine, since we know that the steam in the turbine has very high temperature. So since the steam in the turbine has very high temperature, so that temperature and the water's temperature has finite temperature difference. So due to this temperature difference we expect the heat transfer. Practically we have insulation in the turbine, but in the case when we are saying that we are having heat transfer from the turbine base steam to the water, we are expecting no insulation and then heat will be transferred. And due to this heat transfer, water will come to the state 3 where it has almost reached to the close to the saturation part. It will have the heat which is latent heat getting added into the boiler or steam generator, and then the water which is the dry saturated or superheated water will get expanded into the turbine and it will come back to the condenser. This is a thought experiment. In this thought experiment we are expecting that we will have 1 to 2 as the pump work and 2 to 3, we are saying 2 to 3 is the heat is getting transferred from the turbine. This turbine is giving this heat such that water is going from 2 to 3. Then 3 to 4 is what we are adding heat into the boiler. 4 to 5, earlier turbine was having isentropic expansion which is adiabatic reversible, but now we are saying that there is no insulation. Since there is no insulation, the process is not adiabatic, but there is heat loss, so entropy will decrease. So we are coming back in this manner and not like vertical line, and then we will come to the state like this 5, okay, and then we will have condensation from 5 to 1. This is how the thought ideal regeneration process would execute. Then how to find out pump work and turbine work? It is very simple. Pump work is same, Wp is equal to H2 minus H1, correct. Now what is turbine work? This is little tricky, since what is happening over here is we have H4 minus H5. This is the enthalpy drop of the steam. H4 minus H5 is enthalpy drop of the steam. But what has done with this drop? This drop was helpful for two things. Thing 1 is to increase the enthalpy of water from H2 to H3, plus it has done turbine work. So this is the energy balance. So this was the energy which was available due to the drop of the enthalpy of the steam in the turbine. But this turbine based enthalpy drop of the steam has two reasons. One is heat transfer to the water, another is turbine work. So we can know turbine work is H4 minus H5 minus H2 minus H3. So we can find out turbine work. So we actually would find out the turbine work, but then the issues with such operation of the Rankine cycle is that reversible heat transfer is not possible in finite amount of time. The process is very fast over here, still we have suppose certain amount of time, but in this process we cannot efficiently transfer the heat. So difficult to have turbine as a heat exchanger. So the process of turbine, as what we expect, is an expansion process. So we cannot expect turbine also to act as a heat exchanger. So we cannot have an ideal execution of the regeneration process like this what we have just now discussed. Now this also has led to one more problem, that we have very high moisture content in this state 5. So turbine is experiencing very wet steam, and since it is wet we are having problem of the life of the turbine. So also it is not a good idea. Then there are some other ways by which we can consider regeneration to be possible. The one way is, here we can mix the extracted steam directly into the water, and the process would be executed in this way. We will have process 1 to 2 in the pump, then after pumping in the process 1 to 2 we will have pumped water coming into one chamber. We call it as feed water heater. So we will have feed water heater. So we will have water coming into the feed water heater, and it is basically at certain pressure, which is P2, but we will extract the steam from the turbine at the same pressure, P2 is equal to P6, and directly mix it with the water. So we have P2 equal to P6, and then we will directly mix the steam with the water, and then we will get steam at state 3, and at state 3, which is a dry saturated liquid, and that dry saturated liquid is basically pumped with further higher pressure, rather that is the boiler pressure, and then in the boiler we will have heat addition till state 5 from 4, and then we will have turbine. But in the turbine we actually at state 6 we would have extracted some mass M1, but after state 6 we have rest 1 minus M1 mass is getting flown into the turbine for the expansion process. Initially we had complete 1 kg of mass, 1 kg per second mass flowing into the circuit. So this is how the thermodynamic cycle would look like. Earlier, whenever we were drawing TS diagram for the steam turbine cycle or Rankine cycle, we never have considered any masses. We have just considered the TS diagram, thermodynamic properties, since in the complete circuit we have same mass flow rate, but now we do not have same mass flow rate. What is happening is, till this point we have unit mass flow rate, but at point 6 we have mass getting split into M1 mass and 1 minus M1 mass, and this 1 minus M1 mass is reaching to the condenser. So condenser also has 1 minus M1 mass, this pump also has 1 minus M1 mass, and this feed water heater also has 1 minus M1 mass. But this process 3 to 4 has now 1 kg of mass in pumping, and then this boiler also has 1 kg of mass in the process 4 to 5. So we have defined masses, or rather we have to define masses in this process for the circuit, since it is very essential, otherwise the calculation would be wrong, since we would not be conserving the mass. Okay. So 1 to 2 is a pumping process. At state 2, when liquid water comes, it has pressure P2. Parallelly, steam would have come from 5 to 6 state, but pressure P6 is same as pressure P2. So we will take M1 mass of the steam at state 6 such that it will lead to a state 3 after mixing with water. So mass of M1 is very important, since the same amount of mass M has to be taken from the steam, which would fetch the water plus steam mixture to state 3, which is the dry saturated state corresponding to pressure P2. Then at 3, since steam has mixed with the water, we have pumping from 3 to 4, and then we have boiler from 4 to 5, and then we have basically 5 to 6 has complete expansion, but then 6 to 7 has rest of the mass, which is 1 minus M1 will mix, and 7 to 1 is a condensation process. So this is something which is realizable, this is something which is practically feasible method of regeneration. But then how to find out pump work, turbine work, mass M1? Here pump work finding is simple. So we have Wp is equal to H2 minus H1, but this was the enthalpy rise, but enthalpy rise was for 1 minus m1 mass. We know in the steam table when we take enthalpy, that enthalpy has unit kilojoule per kg. Our turbine work output is also kilojoule per kg. So for that we have to multiply by kg. We are not having unit mass flow rate through this pump, so condenser pump. So we have to multiply by mass, which is 1 minus m1. So then we can get Wp. What is Wt here? Wt is simple, which we have H5 minus H6, but this is the complete expansion of unit mass, but rest of the mass, which is 1 minus m1, will expand from H6 to H7. This is the expansion of rest of the mass. So first expansion plus second expansion. Such formula we had also considered for reheating, where actually we had two turbines, but here we have only one turbine, but there is change in mass. There in reheat we had high pressure and low pressure turbines. Then we can find out basically Q in is equal to H5 minus H4, and Q out is 1 minus m1, since condenser has received 1 minus m1 of mass, H7 minus H1. So now our duty is to find out m1. So we have to write mass balance, and then we got that m1 mass is required to fetch the water from 2 to 3 after mixing with steam. So we can write the energy balance for this state. We know that we have 1 minus m1 mass of water at state 2, and that mass of water is mixing, so plus with m1 mass of steam at state 6, and then both of them would go to state 3. So this is the mixture's total enthalpy. So this is the inlet enthalpy of water plus inlet enthalpy of steam. This is outlet total enthalpy. This is inclusive of all the mass and energy conservations. So we have H2 minus H2 into M1 plus M1 into H6 is equal to H3. So we have M1 into H6 minus H2 is equal to H3 minus H2. So we have M1 is equal to H3 minus H2 divided by H6 minus H2. So we have M1 is equal to H6 minus H2 divided by H3 minus H2. Sorry, we have M1 is equal to H3 minus H2 divided by H6 minus H2. This is mass of steam which is bleeded, which is taken out from the turbine. Then knowing this mass M1, we actually can find out all these quantities. Then we can find out specific steam consumption, which needed W net. We know W net is equal to Wt minus Wp. We have calculated Wt, we have calculated Wp, then we can calculate specific steam consumption. Similarly, we can also find out efficiency, since we know efficiency is equal to W net upon Q in, where we have found out Q in and we have found out W net. But then the feed water heater which we have considered at this moment is called as open feed water heater. Open. The point to be noted in this feed water heater is this is open, that is why the steam is mixed with water. So there is a mass which is coming inside, and then these two masses are mixing. But the constraint is this P6 has to be equal to P2. If pressures are not same, then there is irreversibility due to pressure imbalance, and then mixing process would become more and more irreversible. So to avoid this, we try to maintain same pressure. Then other option is we can have closed feed water heater. In the closed feed water heater, we know we have pump from 1 to 2, and then we have to go from 2 to 3 due to feed water heating. Feed water heating. There is a feed water heater, but it is closed type. What do we mean by closed type? We have water rising its enthalpy from 2 to 3, where steam is dropping its enthalpy from 5 to 7. They are not mixing. Then the steam which has dropped its enthalpy to 7 is sent back through a trap to condenser. This is mostly a isenthalpic process where we have the trap for sending the steam from state 7 to state 8. So this type of feed water heater is called as closed feed water heater. Then how to draw TS diagram. So we have state 1 to state 2 as pumping. Parallelly we have state 4 to state 5 as turbine. So here we are in state 5. Then from 5 we have taken M1 mass for the regeneration process or feed water heating. So this mass is coming and heating the water from 2 to 3. So we reach here, and water has reached here, or steam has reached here, which is a now dry it is a saturated liquid. Now this water is sent to the boiler where we are adding heat from the external source, and this steam is sent back from the 7 to 8 process. And then we have 4 to 5 as expansion partially in the turbine for the complete mass, but rest of the mass 1 minus M1 will expand in the process 5 to 6, and then 6 to 8 we have only 1 minus M1 mass into the condenser, but at 8 or the mass of corresponding enthalpy 8 will be joining to the condenser, and then we have for rest condensation we have complete mass. This is how we can draw the closed feed water heater TS diagram. Then here also we have same problem. Here we have to find out WP. So we now can find out WP. Here pump is handling complete mass. So we have H2 minus H1. Complete mass, it is 1. And then we have WT. WT will be same. We have H4 minus H5, that is for unit mass, plus we have H5 minus H6, but for 1 minus M1 mass. Then this WP and WT is found out. Then we have W net, which is WT minus WP. We have Q in, which is H4 minus H3. We have Q out, which is, this is little tricky since we have two different masses. So we have Q out. In Q out we have 1 minus M1 mass is losing its enthalpy from H6 to H1, and we have M1 mass losing its enthalpy from H8 to H1. Okay, this can also be said to be equal to that we have 1 minus M1 mass losing its enthalpy from H6 to H8 plus complete 1 unit mass will lose its enthalpy from H8 to H1. So these two formulas are practically same. Okay. Then we have to find out M1. M1 would be found out here with the constraint that complete mass of water would get heated, and then its enthalpy will rise from H2 to H3. Complete mass of water would have risen its enthalpy from H2 to H3, but for that what steam of mass M1 has to lose its enthalpy from H5 to H7. So with this formula leads to M1 is equal to H3 minus H2 divided by H5 minus H7. This is how we can find out M1. Then specific steam consumption and efficiency can be found out since we know W net, Q in, these two things. Here, point to be noted that we did not mix the steam which is extracted from the turbine. We did not mix. So, this steam can be at any pressure which we have extracted. There is no constraint on the pressure of the steam.